Hi, welcome to the talk Porting Longhorn over SPDK. So let's start. Starting with a brief introduction to the speaker. My name is Damiano Cipriani. I come from Italy and I'm a software engineer here in SUSE. I am here for more than 1 year. And in the last year, I have worked in the Longhorn team to port this software over a new platform development as SPDK. So let's see the agenda of the talk. First of all, we will present the project. After that, we will talk about what is SPDK. We will show the new architecture with SPDK. We will show a brief comparison results of performance with the old Longhorn engine and new with SPDK, and we will show the roadmap of the future development of Longhorn over SPDK. So let's start. Let's present the project. Longhorn. What is Longhorn? Longhorn is a cloud native distributed block storage for Kubernetes. It uses containers and microservice and create a dedicated storage controller for every volume that the application asks to the software. And what Longhorn do is to synchronously replicate the data written over the volume across multiple replicas that can be stored on different nodes. What is the problem? Longhorn is a very good software, but actually it has a quite long I/O stack. And so this can lead to increase the I/O latency and in a reduced number of IOPS. And so this led to the decision of develop a new engine with SPDK. And so let's see what is SPDK. The Storage Performance Development Kit, that is SPDK, provide a set of tools and libraries for writing high performance and scalable user mode applications for storage. If we adopt SPDK inside the Longhorn, we can, first of all, get better performances. That is the main reason for which we want to use SPDK. Then we can benefit of a wide range of tools that SPDK made continuously available. For example, UBLK that have been released quite recently. And at the end, adopting SPDK, we can get involved in an active community of users and developers, and so we can exchange information, issues, and idea for new development. So, what does SPDK? What can SPDK give to us? SPDK achieves high performance through the use of a number of key techniques. First of all, SPDK move all the necessary drivers into user space, and doing this can let us to avoid syscalls and enable zero copy access from the application. So in this way, we can have in our user space application a buffer that go directly to, for example, to the NVMe disks without being copied in no place in the way between the application and the disk. And so this can be a good thing. Another key technique is that SPDK use polling instead of interrupts. And so SPDK continuously poll hardware for completions. And doing this avoids, first of all, context switch of kernel and eliminate interrupt handling overhead. Another key technique is to avoid all locks in the I/O path. This can be done relying on message passing. For example, if we have many threads that have to share some data, we can give the responsibility to update this shared data only to a single thread, and all other threads can send messages to this thread to make the necessary update of the shared data. And another key of SPDK is that is written in C code. Obviously, to make a better code engineering, we would need higher level languages like C++ or Rust or Go. But that are languages that have, for example, promises and future that can how can I say, that can let us to work in polling mode without be forced to write asynchronous code, because in SPDK quite all of the operations are asynchronous, and in C this means quite always passing a function pointer to a function, and so this can lead to a code flow that is not so easy followed by the developer. But SPDK is a low-level library, and so it needs wide compatibility, and as we said, high performances. And so at the end, they decided to use C code instead of higher level message languages. So let's have a brief look at actual longer engine architecture and to the next one developed with SPDK. So this is the actual engine architecture. As we can see, the data path between the application that run in the pod is quite long before to arrive to the longer engine controller, because we have an iSCSI protocol and a customized protocol. And as we said, this can lead to higher latency and reduce IOPS. And so let's see how this data path can change with the adoption of SPDK. This is the diagram of the new architecture. As we can see, the data path with iSCSI and custom protocol have been substituted with a block storage that is accessed by the application inside that runs inside the pod. And this block storage is created by the Linux NVMe driver that attached to a NVMe over Fabric target exposed by SPDK. So if I write over this Linux block device, the data arrives directly to the SPDK target. What do SPDK target? It expose over the NVMe over Fabric target, the interface, sorry, the RAID 1 BDEV. A BDEV is let's say a new unique interface used inside the SPDK to handle different kind of of disk and of storage. And inside SPDK, we create a write1 BDEV that receive the read and write operation from the Linux block device and split the operation over multiple replica of the same data. In case of a write operation, it replicate the data over all the replica. In case of a read operation, it has a round robin technique to split the read between different replica. Every replica is a BDEV that is created attaching, in case of a remote node, to a NVMe over Fabric subsystem exported by the remote node. And so we attach to this subsystem and create a local BDEV that is a logical volume exported from another node. The logical volume is created inside a logical volume store that we have inside the SPDK target, and every logical volume store is coupled with a SSD disk over the node. Instead, on local node, the local replica is not attached to an ME over Fabric subsystem, but is attached directly to the logical volume of the logical volume store of the local SPDK target. And another thing that we can say is that in the future, this part of the architecture may change, because actually using a NVMe over Fabric interface to expose a local BDEV in the machine for creating a block device can be quite weird, let's say. And so in the future, if we will use, for example, UBLK, we have the possibility to change this part, and so to reduce the complexity of this part of the software, the data path will be shorter, and I think that maybe even the performance will be increased. Another thing that we can say is that actually we don't use the NVMe driver that is inside SPDK. That is a user space driver, lockless, that works in polling mode, and that attached directly to the SSD disk, telling the Linux kernel that this is a hardware that is controlled by this driver, and so tells the kernel to detach from it. But actually, we don't use this functionality. Actually, we write over the block device that is created by the Linux NVMe driver that control the disk. But in the future, maybe we will change this. So let's go further and have a look at the performance results of actual Longhorn engine and the future with SPDK. So the details have been done with these tools called Kbench, that is fundamentally a wrapper or FIO. And these are the details of the test done, like the machine, the cloud provider, and the operating system. So let's have a look at the numbers. And we have done the comparison over a single node that is local with the SPDK target. So we have a logical volume that is inside the same SPDK target. We have done a comparison with a single node but remote, so on another node, and with two remote node. For the local node, we have put even a comparison with the raw disk numbers. And as we can see, in all the three scenarios, the IOPS and the latency show quite an increased performances respect to the Longhorn engine. We can see that IOPS and latency in single node, in local, in single node remote, and in double node remote, we can see an increased performances. And what can we say is that the increased performance is we can see better this increased performance in the single node local, because when we go to a remote node, we have the network latency that is common between Actor Longhorn engine and the SPDK engine, and so we can see that the percentual increase of the SPDK is lower. And so, what else? After showing the result comparison, we can discuss about the roadmap of our project. So, we can show now the development done of SPDK for the first experimental version of Longhorn with SPDK engine. The first experimental version will be 1.5.0, then will be released at the end of this June. And what have we done in this release? First of all, volume management. And what we have done, we have made some changes to the RAID 1 SPDK implementation to allow a RAID 1 with a single replica that was not allowed by SPDK, but that actually Longhorn support. So we have made these changes. After that, we have done a development to pause and resume I/O over the block device. Why we have to pause and resume? Because let's suppose that we have to make a snapshot over a volume that have more than one replica. The snapshot feature of SPDK has a freeze feature. When you make a snapshot over a logical volume, the software freeze the I/O, create the snapshot, and then restart the I/O. But the freeze is done only over the blob, the logical volume that is involved in the operation. But if we have more than one replica, we have to make the snapshot over all the replica. And so we have to pause the I/O, make the snapshot over all the replica, and after that resume the I/O so that all the snapshots have the same data. We would need another feature that actually is not available in SPDK. After pausing the I/O, we would make a flash over the logical volume that we want to snapshot. But actually, blob store of SPDK does not let the flash I/O operation. And so the only way that we can do actually is to pause the I/O, wait some time, the time that the SPDK need to complete all the ongoing operation. After that, make the snapshot and then resume the I/O. But in the future, we will implement Flash 2. And another feature that we have developed for this Longhorn release is the offline rebuild. Because how can I say, in RAID we have the RAID that is created with different volume, but the RIDE works only over the real data of the volume. Each of these volume can have a snapshot stack. So when we have to rebuild a node, a failed node, we have to recreate all the data that node had before the fail. But we cannot simply write all the data that we read from another volume of the same RIDE, because the data have been distributed in different snapshots. And so we have to recreate the entire snapshot stack of that volume. And so we had to develop a new functionality in SPDK called shallow copy. And with this functionality, we can copy only the data that rely on a single snapshot of a volume over another BDEV. In this case, the BDEV will be another volume exported from another node. And so in this way, we can recreate the entire snapshot. Let's see now what are the development that we will do to implement the feature parity with actual Longhorn engine. And so we will have the next release 1.6.0, I think at the end of this year, where we will have, as discussed before, IO flash that will be implemented using a new API added recently to SPDK like LVOL Quiesh. And another big development that we will do for next release is online replica rebuild. That is the rebuild of a node without detaching the volume that have a replica over that node. Actually, we can do the rebuild only in offline mode, so stopping the volume, make the rebuild, and then restart it. So the application cannot use the volume during the rebuild. What we will do is the online, and so the application can continue to read and write over the volume without stopping. And a couple of other development that we will do is data integrity, so that can be useful in case of node failure, and volume trim to release not more used volume data by a single volume. So these are the references that you can have a look to learn a bit more about SPDK, Longhorn, and Longhorn SPDK engine. That's all. Thank you for participating to this talk. Bye.